Calculus, video 66, summation. So we use summation to add several or even infinitely many numbers together. It's not really a calculus topic of its own, but it is something we're going to use in calculus here in the next couple of lessons. So we're focusing on summation here just to kind of as a tool that we're going to be using shortly. So a little bit about summation. First of all, the notation for summation. If we want to sum or add several things together, we use a capital sigma notation. So typically we write the sigma notation looks something like this. This is a capital sigma, Greek letter sigma. And what it means is when the things that come up after that, you want to sum those things. So, for example, we might want to sum using the sigma notation. And actually, if you write it nice and fancy, it's got little lines here and here. But in math, we typically write too fast for that. We just kind of write the first way I have it here. Along the bottom is what's called our index. So we're going to have, in this case, I'll use the letter I. I equals 1. And what this is the starting. This is where we're going to start. And at the top number is where we're going to end. So maybe I'll go from I equals 1 to 4. All right, that's where we're going to end. Of 3i. And so and the I here is just a variable. It's what we call like a dummy variable. It doesn't really mean anything. It's an index or a dummy variable. So I didn't have to use i's here. I could have used j's or k's or any other letter really. But what it's saying is I'd like to have all the i's. We're going to start with 1, and so I'm going to start by plugging in 1 into the I. So it's 3 times 1. And then because it's sigma notation, we're going to then add that to the next term. And we're always counting by ones. And so we start with I equals 1, and then the next one is what happens when I is 2. And so that's 3 times 2, plugging 2 now in for the I. And then moving up by 1 again, right, started with 1, and then it's 2, then it's 3, so I'll plug 3 in for the I, 3 times 3, and then add that to plugging in 4 into the I. And that's where I stop, right? That top number up here, that tells me my ending. So this looks something like 3 times 1, and since it's sigma notation, that tells me I'll be adding the next term to it, 3 times 2, plus 3 times 3, plus 3 times 4. And the number at the top says I stop at 4. I start at 1, I end at 4, and I always move by ones. Okay. And I add or sum all of those numbers. So the sum, we say from I equals 1 to 4 of 3i, the sum from I equals 1 to 4 of 3i is 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4. That's 3 plus 6 plus 9 plus 12, which looks like about 30. And that's it. That's summing from I equals 1 to 4 of 3i. Okay? And we can do that for different things, not just for 3i. We could do it for other things. I squared minus 2i plus 1. 4 to the power of I, the sine of I, right? You can use whatever sort of function, if you will, in place of 3i. And again, it doesn't have to be I. In the next example, I'll use a k, just to kind of switch it up. And also, it does not always have to start at 1. You can make that starting value whatever you want. You could start it at 0. You could start it at 3 or 4 or 2. And the ending value can be also whatever you want as long as it's more than your starting value. So, for example, in the next case, let's try this one. The sum, all right, the sigma notation again means to sum, to add, from k equals 2 to 5 of k squared minus 3k plus 1. So once again, we're going to start with the k value of 2. We're going to plug 2 into every k that we see in the k squared minus 3k plus 1. And then add that to plugging 3 into all the k's. Plus, plugging 4 into all the k's. Plus, plugging 5 into all the k's, and that top number tells us where we stop. So it looks something like this. I'll start by plugging 2 into all the k's. 2 squared minus 3 times 2 plus 1. Now I'll add that 2, and again we know we're adding here because it's sum. Sigma notation means to add. Now we'll plug in a 3 into all the k's. 3 squared minus 3 times 3 plus 1. Now we'll plug in 4. 4 squared minus 3 times 4 plus 1. And then finally plug in 5, sub in 5. So 5 squared minus 3 times 5 plus 1. And if I work that out, I get 2 squared is 4 minus 6 plus 1 plus 9 minus 9 plus 1 plus 16 minus 12 plus 1 plus 25 minus 15 plus 1. That would be negative 1 plus 1 plus 4 plus 1 is 5 plus 10 plus 1 is 11. Negative 1 plus 1, 0 plus 5 plus 11 equals 16. Okay, very good. Let's just try a couple more, at least one more. How about the sum? Let's start it at 0 this time, and I'll go back to using i's. I equal 0 to, say, 4 of 2 to the power of I. All right, go ahead, pause the video, try it out, see what you get. All right, so 2 to the power of I. So we're going to start with 0. That'd be 2 to the power of 0 plus 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3 plus 2 to the power of 4, and that's when I stop. So 2 to the 0 is 1 plus 2 plus 4 plus 8 plus 16. That's 20, 31, I believe. Okay, very good. So these sort of exercises are really just about getting us used to using the summation notation. But did you know there's actually a multiplication notation as well? If I wanted to say multiply the terms, the symbol there is capital Pi. All right, we like to use the same symbols for multiple things in math. If I were to say pi of I equals 0 to 4, 2 to the I, it's the same terms, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, but now, instead of summing those things, we multiply those things. That would be 2 to the 0 times 2 to the 1 times 2 to the 2 times 2 to the 3 times 2 to the 4. That would be 1 times 2 times 4 times 8 times 16. That one I'm not going to try to do in my head. Yeah, we'll just let the calculator work that one out. 2 times 4 times 8 times 16 is 1,024. All right. So if you see the pi symbol, we're say multiply the terms. If we see the sigma notation, the sigma symbol, it means to sum or add the terms. Very good. All right. Let's go ahead and kind of do the opposite now. Now, in this particular class, we're not really going to be multiplying the terms. Just wanted to let you know that is out there. We don't just have a summation notation. We also have a multiplication notation, a product notation, if you will. We are going to focus on the sigma notation of summing. And this time, what I want to do is kind of work it backwards. Again, just with the idea of we're trying to understand and become familiar with this summation notation, is I'm going to give you the right-hand side here, something like 1 plus 2 plus 4 plus 8 plus 16. And I want you to be able to rewrite it as the sum, I equals 0 to 4 of 2 to the I. I want you to kind of go backwards. So let's try it this way. 1 plus 3 plus 9 plus 27 plus 81. How could I write this in sigma or summation notation? Pause the video, see if you can work it out on your own. Okay, well, we know it's summation because I'm adding the terms together, so sigma. I'll use i's. I is equal to, we need a starting value for the I. And what we're noticing is, for each term, I have a 1, then a 3, then a 9, then 27, then 81. Each term is 3 times what the previous term was. 1 times 3 is 3, times 3 is 9, times 3 is 27, times 3 is 81. And that tells me, since we're multiplying by the same number each time, that's going to be an exponential function. In fact, I'll fill in the lower number here and the upper number in just a second. But this, I'm thinking, is going to be 3 to the power of I. Each number is 3 times what the previous number was. And now, since I kind of have that pattern, I want to make sure my starting number is right. And so what does I need to be so that my first number is 1? Well, anything to the 0 power is 1, so I needs to be 0. That will give me 3 to the 0 is 1. And my last number needs to be 81, so 3 to the 4th is 81. So 1 plus 3 plus 9 plus 27 plus 81 is the sum, I equal 0 to 4 of 3 to the I. Okay. And sometimes you'll have it written like this. Well, where they'll say something like 1, 2, 3, 4, 5. The first 5 terms are, the first 5 terms of the summation, or of the sum, are 1, 3, 9, 27, 81. And instead of using the addition sign, meaning like these are the terms that we would be adding together. So you might see it like that, but again, you're just trying to find the pattern. Let's try one more. How about the 1, 2, 3, the first 6 terms of the sum are 1/5, 1/7, 1/9, 1/11, 1/13, 1/15. Or I've included the word first on both of those. Really what I'm meaning here is, I'm going to erase this, not just the first 5 terms, but the 5 terms of the sum. So I have 5 terms. Later on, we'll move into first 5 terms. We'll try and get a pattern, and we'll talk about what happens as we not just have the first 5, but we have the rest of them as well. If we have more of them. But in this case, I really just had 5 terms. So the 5 terms of the sum are, the 6 terms of the sum are, that seems better. So let's go with that. Can you, from these 6 terms, like they were being added together, right? Can you create a summation from that? Right, pause the video, see if you can do this. Okay. One thing you'll notice is there's a 1 on top, and then all of these numerators, so probably a 1 on top here. And just for fun, I'll use case. Now I need to get a 5 as the denominator the first time, and then a 7, and then a 9, and then an 11, and then a 13, and 15. So what I'm noticing is my denominator is 2 more than the previous denominator. It's 2 more than that. So it's like I'm adding 2 to each denominator. And since I'm adding 2 each time, think about doing 2 times k. Because if k is 1, then I'm adding 2. It's at 2. If k is 2, then it's at 4. If k is 3, 2 times 3 is 6. If k is 4, 2 times 4 is 8. Right? So I get 2, then 4, then 6, and 8. And I'm adding by 2 each time. If you're adding by 3, think about 3k. If you're adding by 5, think about using 5k. Now, I need to make sure I have the right starting value here. So, because there's actually a couple different ways you could write this that would be correct. Let's say I wanted to start with k equals 1. Okay. If k is 1, then I have right now 1 over 2 times 1, so 1 over 2. But what I need to make it is over 5. So I would need to do 3 plus 2k. That way, if I plug k in as 1 the first time, I get 5 in my denominator. So k would need to start at 1 and end at 6. Because if k is 6, that's 2 times 6 is 12, plus 3 is 15, and that's my final term. So I would need to go from k equals 1 to 6 of 1 over 3 plus 2k. That would be one summation that would work. But there's another one that would work. What if instead I had the same sort of setup at the beginning, and I have a 2k here, because I know I'm adding by 2 in my denominator. But this time I'm going to let k start with 0. Now if k is 0, 2 times 0 is 0, and so my initial starting value, I would need to have a 5 right there. All right, so if k is 0, I get 1 over 5 plus 2 times 0, that's just 1 over 5, that's my first term. My last term ends at 1 over 15, so to make that work, k would need to end at 5. Right? If k is 5, 2 times 5 is 10, plus 5 is 15. That gives me my ending term. So these, although they're different, really represent the same 6 terms. I can go the sum from k equals 1 to 6 of 1 over 3 plus 2k. Or I can go sum k equals 0 to 5 of 1 over 5 plus 2k. They really are the same. All right, let's try one more. So either one of these are correct. Notice that 1 to 6 is 6 terms. 0 to 5 is also 6 terms. Right. Last one, same idea. I'll give you 5 terms this time. 1, 4, 7, 10, 13. Okay, what do you think this sum is? Hopefully you noticed that we're adding by 3 each time. Last time we were adding by 2 in the denominator, and the numerator stayed at 1. This time we're just adding by 3. So the first thing I'm going to think about is there's probably going to be a plus 3k in there somewhere. That allows me to add by 3 each time. And then I just need to make sure my starting value is correct. So depending on what I want to let k equal here, let's start with, let's say k is 0. Sometimes that's the easiest. And if k is 0, then 3 times 0 is 0. That means I just need a starting value of 1. So when k is 0, 3 times 0 plus 1 is 1. Then I need to end at 13. So you can kind of figure out what it would be, what the k value should be, or think about it like this. There are 1, 2, 3, 4, 5 terms. That means I know I have to end at 4. Because 0, 1, 2, 3, 4 is 5 terms. And you can check it out. If k is 4, I get 1 plus 3 times 4, 3 times 4, 12, plus 1, 13. That works. You could have also done something like this. K equals 1 to 5, that's 5 terms. Adding 3k, but if k is 1, that's adding 3, that means you need to start at negative 2. All right, if k is 1, then it's negative 2 plus 3 times 1, negative 2 plus 3, that's 1. That also works. Okay, very good. So hopefully that helps us kind of give a good understanding of summation and just gives us some familiarity with using it. But let's move into one last part of this. And it's this statement here, and this is really important. Most of the time, what we're going to be using these summations notation for is not exactly like the sum is k equals 0 to 4 of 1 plus 3k. A lot of times, we're using that summation as either subscripts or superscripts for variables. So it might look more like this, right? So we might think that we have this sum of, I'll use i's, I equals 0 to 3 of a sub I, the subscript I, x to the power of I. At this time is both a subscript on a sub I. That's actually, a here is a number. A sub I is a number. A is a variable. A sub I is a number. And then x, a variable x to the power of I. What this is a representation of a degree 3 polynomial. And you might be thinking, okay, how is this a representation of a degree 3 polynomial? Well, the a sub I is acting like the coefficient, and then x, the variable raised to the power of I. This is letting I equal 0, I get a naught, or a sub 0, x to the 0. And then I'm summing the next term plus a sub 1, x to the power of 1, plus a sub 2, x to the 2, plus a sub 3, x to the 3. And this it's just it's a polynomial of degree 3, right? This is a degree 3 polynomial. X to the 0 is just 1, so maybe we rewrite this as a sub 0 plus a sub 1 x to the 1 plus a sub 2 x to the 2 plus a sub 3 x to the 3, where a naught, a1, a2, a3 are the coefficients of the x terms. And so this degree 3 polynomial can also be written using our summation notation. And honestly, that's more the direction of how we're going to be using summation notation, is more along the subscripts kind of idea. Not exclusively. We'll also use it as just, having an I in there, but we should recognize that this also plays an important